Hi there, Rachel Sherman here, and in this video we're going to take a look at when using proof by cases is a necessary method. This is something that we tend to get to more so in set theory proofs, but it can be used for proofs about integers as well, when you have something kind of vague and you maybe need to verify that something works regardless of the type of integer, such as you check when it's even, you check when it's odd, and if both of those proofs pan out, then you can say that it would work for any integer. So proof by cases, when are they necessary? Pretty much any time there is one or more situation, I guess technically two or more situations, right? Two or more situations that you would have to check. So like the example of checking something being even and odd. When we get into set theory proofs, there are places where you have to basically show how when you dissect the sets, through their unions that you're guaranteeing something exists in those sets regardless of which portion it's in. So it's really just a way to kind of cover all of your bases and make sure that you're showing something works regardless of its background circumstance. So here's an example I like to share that is kind of just getting our feet wet with using a proof by case. So we're going to prove that the absolute value of a real number is always greater than or equal to 0. So something to make note of here is that the absolute value function itself is defined as a piecewise function. So there's actually two components to it. The absolute value of a real number x is equal to x when x is greater than or equal to 0, and it's equal to negative x when x is less than 0. Now, what this tells us, and kind of why we would have to prove this using cases, is if we're trying to prove that the absolute value of a real number is always greater than or equal to 0, you have to check and see, well, what does that value actually represent? Which part of that domain are you in? Is x greater than or equal to 0? Is x less than or equal to 0? Or I'm sorry, less than 0. So what's interesting here is that if you're trying to prove any statement with a piecewise function, you have to basically have as many cases as you do portions to your domain. So we're splitting our domain into greater than or equal to 0 and less than 0. So that means two cases for us. To prove this statement, we're going to start out in a very similar way to how most of our other proofs have begun. And that is by, give the background information. What is true regardless? So let's suppose that we have some real number x. So that's all we know for now. Suppose that we have a real number x. Now, we know the absolute value of x is defined by x and negative x depending on what part of the domain we're in. So we will show using our cases that when x is greater than 0, that the absolute value of x is greater than 0, and vice versa. So if we have our first case, so let's call this case 1, x is greater than or equal to 0. Well, if x is greater than or equal to 0, that right there is telling us that the absolute value of x is greater than or equal to 0, since the absolute value of x is equal to x, and we know that x is greater than or equal to 0. So this part of the proof, it's almost kind of comical how simple it is, right? But this, by just writing out what this gives us, is telling us that yes, of course this is greater than or equal to 0, which verifies that the absolute value of x is also greater than or equal to 0. So that's it for case 1. Case 2, pretty close, but a slight variation here. So what happens if x is less than 0? Well, when x is less than 0, the absolute value of x is equal to negative x. Well, we know what's happening for x less than 0, right? So if we're saying that x is less than 0, and you multiply by, let's say, a negative 1, well, what does that leave us with? When you multiply an inequality by a negative, you have to flip the sign. So you have that negative x is greater than or equal to, because it's the opposite of this, 0. So this also shows that the absolute value of of x when x is less than 0 is greater than or equal to 0. So why are cases required in this case? This is really just to illustrate why cases are necessary. Cases are necessary because we don't know which part of the domain it is, and it's almost like a safeguard. We want to make sure that no matter where in our domain this is, that we've covered our bases and we know that it's true regardless of the domain, which is what we've shown in this case. Usually you would wrap this up with maybe just one statement. It can be something simple like, we have verified that this works for all elements of the domain or all cases covering our domain, and then kind of wrap up your thought from there. And from this point, you would just restate, just like you have in most of your other proofs, therefore we have shown that if x is a real number, the absolute value of x is always greater than or equal to 0, and you'd wrap it up. That concludes this video. Thanks for watching.